Okay, going to get temporarily a little off topic, though it's quite related. Something I've really enjoyed trying to understand and explain for really since I was your age. Um, a senior in high school, I remember specifically. Okay, most of what we learn in physics, to me, just makes sense. Things click, projectile motion. It makes sense of throwing balls before they do what you expect them to, and then you can analyze it nicely. So, for the most part, the world just makes sense. Physics confirms that in so many ways, and yet every now and then something comes up, especially in the weird realm of modern physics, or even a little bit earlier than that, where stuff doesn't click. It doesn't make sense to our everyday experience, and that's intriguing. And then in me anyway, and probably in you, it produces this drive to want to get it. Well, the thing I'm going to talk about now, we're going to talk about special relativity, Einstein's theory of special relativity. And this is the right place to bring it in because we've nearly finished or mostly finished our treatment of electricity and magnetism. And his paper was called in 1905, which he wrote while sitting in the Swiss patent office. He didn't have an academic job at the time. Was called On the Electrodynamics of Moving Bodies, just about 5 pages. And it utterly changed the way we looked at things. Uh, and again, it starts with this. Here you see a bunch of nasty math. Some of these things we know. In fact, we know at this point from the way I've been presenting things, where I've chosen to branch off here, we know 3 of these things. I wonder if you can figure out which is which. Or if you guess what that one is. I hope you know. Gauss's law. Gauss's law describes the behavior of the electric field and how it depends on charge. Great. This next one, it kind of has a name. You could call it Gauss's law for magnetism, and it just is zero when you find the flux through a closed surface of magnetic field lines is zero because magnetic field lines form closed loops. There's no magnetic monopoles. That's what that is. What the heck is that? Okay, it's actually called Faraday's law, but we haven't learned it yet, but we will real soon. And we just now learned this one. This is Ampere's law that helps describe magnetic fields due to currents. But these laws form something altogether. They're called Maxwell's equations. James Clerk Maxwell, a Scotsman, way back in 1865, I believe it was, he took all these laws, he wrote them all down. I mean, he didn't come up with any of them. Except one thing, he did add a term to one of them that I'm not going to mention right now. But basically, he wrote them down, he looked at them, he saw them as a system of equations. And he solved them as a system of equations. And I'll tell you what he came up with. He came up with there ought to be these things called electromagnetic waves. That electric and magnetic fields were coupled together, and from a source, like a wiggling electron or something, these waves would break loose and travel through, well, he thought they traveled through something, they figured they had to be this thing called the ether. Something had to wiggle. Waves got to have something to wiggle, don't they? But anyway, figured they had to be a medium, and he calculated the speed they would go. And the speed they would go turned out to be they should travel at a speed of 3 times 10 to the 8th meters per second. You could figure that out from the math. I'm not up to the task of solving this now and figuring it out, but he did, and he got the speed would be 3 times 10 to the 8th meters per second. And people knew what that number was. That was the speed of light. The speed of light. Speed of light relative to what? Your flashlight? Somebody else? Interesting question that we will come back to shortly. I'll be erasing this in a minute. But so we have Maxwell's equations. Maxwell predicts electromagnetic waves. Light. And of course, people already knew about light, but they didn't know it was electromagnetic waves. They suspected it was some kind of waves, but had no real good reason to believe it had to do with electricity and magnetism. Maxwell predicts that. And by the way, by doing that, He's given us all this telecommunications, but the way you're watching this right now, electromagnetic radiation, this is a big, big deal. I should say more about that later. But in any case, let me get more to my point. Remember the thing we came up with the other day? We explored, the two charged particles travel in parallel, and we found that they would have an electrical repulsion, and yet because they're traveling, they would have a magnetic attraction, and the magnetic attraction would increase with their speed, and conceivably it could get strong enough to keep them from moving apart at all, so they travel in parallel with each other. And what speed would that happen at? Well, by using essentially the bones of the Biot-Savart law, when equating it to Coulomb's law, we usually kind of like something to do with that, something to do with that. We found that the speed that they would have to go to not go apart from each other was c. If they went the speed of light, the magnetic force would equal the electric force, and they would travel in parallel forever. It's intriguing. What I'm doing, I'm taking puzzle pieces and putting them kind of ready to make you want to solve the puzzle. So we've got that. But another question that will come up here is, who says there's any magnetism? I do. I see two particles fly by. Look at that. And I know how to do a little right-hand rule and get my direction of the field. I know how to calculate the magnitude of the field. And you use v, the speed. So I say there's a magnetic force of attraction between these particles. I say that as I watch them move by. But did you ever ask them, what does this particle think this particle is doing in its world? And I think you understand relative motion to some extent. Sometimes in introductory physics courses, it's an idea that we have to work on, but you've probably already got this down. It's called Galilean relativity. The idea that who's to say who's moving? If I'm riding in a car throwing a ball up and down, and it just comes back down to me, I'm not mystified by why it doesn't fly through the back windshield. Why should it? In my frame of reference, it wasn't moving. So what? Somebody outside can think it's moving. They can watch it travel in its projectile path. You got that, I think. Again, Galilean relativity, the idea that motion's a relative thing inherently. So that's not bad. Most of us can't handle that. But that means according to these particles, there is no magnetism, because after all, they're not moving relative to each other. This particle doesn't think this one makes a magnetic field. I think it makes a magnetic field when I watch them fly by. I think they both make magnetic fields and attract each other with their magnetic fields, but they don't think so. So is magnetism even real? It's a good question. It's a really good question. And we're going to get to the answer. So we're about to explore special relativity. And in case these little weird connections and conundrums didn't do it for you, I like to tell a story. It's a true story, or would be if it happened. Okay, that kind of story. It's a realistic story, given the assumptions. You got two identical twins. I give them names, I don't know. I was going to say Alice and Bob, but they wouldn't be identical, probably. And then they both start with A. Anyway, twin 1 and twin 2. We'll just give them names like that, point names. So twins 1 and 2 are the same age. Obviously, they're twins identical. And on their 20th birthday, they hear about there's free tickets to fly to Arcturus in the super duper spaceship that goes real fast. In fact, the spaceship goes 99.999999, total of 8 nines, including the ones before the decimal, percent the speed of light. And Arcturus is 40 light years away. And if you know what a light year is, the distance light goes in a year, then going within a 100 millionth or whatever part of the speed of light, you'd take pretty much 40 years to get there. And you get there and ain't nothing around there to look at, so you immediately turn around and come home at the same speed. You should be gone for just barely over like 80.0001 or something years. And so say twin 2 gets to go. Twin 1 stays home on Earth. Twin 2 gets to go. Twin 2 takes off at that speed, goes to Arcturus. Ain't nothing there to see. Turns around and comes back. What I'm going to tell you is that twin number 1 waited for her sister for 80 years and became 100 years old. And on the day of her 100th birthday, she has her cake with, oh my God, 100 candles on it. She's going to blow that out at age 100. She does. Good for her. Anyway, then she's wheeled down, by now probably a little disabled. So she wheels down to the spaceport and waits for her sister to come home. Her sister lands, and lo and behold, her sister is still 20 years old. In fact, her sister has aged 4 days. She's only had 12 meals, not had a haircut, looks the same, feels the same, only slept 4 times, plus a couple naps maybe. Took clocks of all different kinds, mechanical, electronic, nuclear, whatever clocks, atomic clocks, took them along. They all said it's been 4 days. She planted a little bean plant, a little milk carton. It's barely sprouted. It's been 4 days for her, and it's been 80 years for her sister. This is called the twin paradox. It's quite famous. The reason it's called a paradox, we have yet to see. I haven't said why it's a paradox yet, or how that paradox gets resolved, because fun is in resolving it. But in any case, weird stuff happens. There's a bunch of other things. I'm going to tell you about the pole in the barn paradox. I'll tell you about the 3 psychics in a park while the Andromeda Galaxy rises and the Andromedan, Space Command or whatever. So I'm going to have some stories mixed in with this, and it's good stuff. Where are we going to start? Okay. Einstein got to thinking, one thing he thought, Galileo thought, you and I think, and that is this assumption, this postulate, is Einstein's postulates. Now, postulates are things that you postulate. You put them out there for starters. They're starting assumptions, and you work from them. Do you prove them? Maybe, but not right now. Right now, we take them as postulates. I'm going to give evidence for each one, but in any case. So the first postulate is really just, I'm going to put it this way. Motion is relative. Or you can't say who's moving, or something like that. And that really goes back to Galileo. Galilean relativity. That goes way back. The second one is one that is not at all obvious. In fact, if you really think about it, it sounds messed up. But if you think about it more, you realize it pretty much has to be true. I'm going to say it this way. I don't think that's how Einstein said it. It can be said in some different ways, like the speed of a wave is independent of the motion of its source. Now, why that's logically connected, you can get into. But in any case, this is basically what we're going to use as another postulate. The speed of light is the same for everybody. Well, of course. Everyone's created equal, all that. Everybody deserves to have the same speed of light, right? What kind of a universe would give some people one speed of light and other people another speed of light? Sounds egalitarian, doesn't it? And it is. In fact, Einstein thought it just wasn't right. Okay, first of all, mechanics. Mechanics had already dealt with this. The motion is relative thing. I'm riding in the car, tossing the ball up and down. The ball's not moving relative to me. It does this. And it's a completely consistent account with somebody else watching the car go by while it goes like that. That's not a problem. Mechanics, Galileo even had dealt with that. That's easy. But the electricity and magnetism, you've already seen just a moment ago an example of it being messed up about motion being relative, because the 2 particles flying past each other that I believe have a magnetic attraction, they don't think so. What kind of a world is that? In which a force exists for some people and not for others. That ain't right. Einstein didn't think that was right. And Einstein wanted to basically extend Galilean relativity to the relatively new world of electricity and magnetism, which was intimately tied in with light. Because remember, Maxwell predicted the speed of light from his equations, other people's equations that he predicted from, and found it was it was just the speed of light, period. That's it. Now, by the way, there's the speed of light in a vacuum, there's the speed of light in different substances, but notice this. Nobody said in there what the speed was relative to. Maxwell, like anybody, I'm sure assumed that it's the speed at which they traveled through their medium. That medium was called the luminiferous ether. It was a rather difficult to believe in thing, except you had to, kind of. The luminiferous ether, luminiferous ether, was a mysterious substance that had to fill all of space. It had to, because otherwise you couldn't see stars. You know, the way you see a star is the light gets to you. Well, it needed a medium, to get wiggled for the light to get to you, like this sound. It's reaching the microphone of the computer and reaching your ears from there because of air. Want for air. Okay. So this ether was the medium that conducted the sound. But it had to be extremely vaporous and extremely thin. The Earth had to be able to orbit for millions or billions of years around the sun without spiraling into the sun from losing energy to the stuff. So somehow it didn't seem to offer any resistance to motion. And yet, in some sense, it had to be rigid, so that waves could go really fast through it. It was a very self-contradictory sort of thing. And if this were, 130 or 40 years ago, and you were taking a physics class, you'd be taught about the luminiferous ether, and you'd be baffled by its amazing properties, and your professor, teacher, whatever, would be extolling the mysterious virtues of the luminiferous ether, and you just have to know for the test, Now, unknown to Einstein, according to Einstein, though he could have known it if he read enough, a couple of experimenters, Michelson and Morley at Case Western Reserve University in Ohio back in 1883, did an experiment to measure the speed at which the Earth was going through the ether. I'm not going to describe it too much, but it's called a Michelson interferometer. And it was basically a set of mirrors here and you shot a beam of light in. There's an interference phenomenon. We haven't studied waves in this course, so I'm not going to get into that right now. But anyway, it was basically an ether speedometer, or it could tell the speed at which the Earth was going through the ether. And so they happily pointed the thing in the direction the Earth is going around the sun, figuring that's the direction we're going through the ether. And they got an answer, and the answer was 0 for the speed. Odd result. You'd thought it might be like 70,000 miles an hour, maybe. But it was 0. Oh, but there's a possible answer. Could be that there's an ether wind blowing at your back, like you're running around a track and you got the wind at your back. You don't feel it, but you know what happens when you come around the turn, down the other straightaway. Whoosh, maybe you know that. Wind hits you in the face. You get like 140,000 mile an hour ether wind 6 months later. They check 6 months later, 0. What the heck? Is the ether wind following us around the sun? Or maybe the geocentric theory was true. Maybe the Earth doesn't move, the sun goes around us. Ooh, that's mighty conspiratorial. How about there's no ether? That leaves you wondering how the heck the waves could travel, but what if there's no ether? Now, the story would make great sense if I told you that Einstein knew this and was trying to figure this out, but he didn't, according to him. Now, also, there was a guy named Lorentz who at the time came up with a set of equations that actually purported to show deformations of things due to pressure from the ether wind. It was a set of equations to make things make sense between space and time, but his interpretation was basically that, maybe things get smushed by pressure with the ether. He still believed in the ether, but pretty hard to resolve. So, I want to talk just a little bit more about the weirdness of this. For the speed of light to be the same for everybody, first of all, it's kind of good to get ether out of the way, because that way, where is it? Maybe it'd be better if there were ether. But if there's not any ether, now you have the problem. Think about this. What if I come running at you, tomato? I'm driving in a car at you with a tomato. I've been practicing throwing tomatoes. I throw them at 30 miles an hour every time I throw them. I spend my Friday nights cruising around throwing tomatoes at innocent bystanders. and I'm going 40 miles an hour in the car, and I throw a tomato at 30, you know it's going to hit you at 70 because, add up the speeds, right? Relative frames of reference and all that. So I throw it at 30 out of a 40 mile an hour car, add vectors 70. Fine, sure. But what if it's light? I come flying at you in my space cruiser at 90% the speed of light, shoot a beam of light out, which leaves me at the speed of light. How fast does it hit you? If you followed the tomato example, you'd say 1.9 C, because I'm going 90% the speed of light, add 100% the speed of light, go for light, it's 1.9 times the speed of light. But wait. Everybody gets to see light going the speed of light. You can't have somebody, just because they're an innocent bystander, get hit by light that's going faster than the speed of light. So then you say, oh, I get it. It's like waves. Maybe it only left me at 0.1 C. Maybe that's it. Yeah. So 0.9 plus 0.1 makes 1 and hits you at the speed of light. That's not fair to me. I have to see it leave at the speed of light. You got to get hit at the speed of light. In other words, we kind of need 1 plus 0.9 to equal 1. What kind of math is that? Well, it's kind of got to be that way. Because if everybody's going to get to use Maxwell's equations and predict the speed of light, there's no universal thing to measure it with respect to. It's with respect to you and to me. And we got to resolve that. Let's see how that works. Something has to give. That's kind of the bottom line. And here's how it goes. If I take these two postulates and apply them to an interesting little example, I'm going to get all kinds of insights. So my example is this. I probably got it from some book. Oh, I forgot to mention. When did I get in this? I got into this as a senior at Woodward Academy. I remember why. Oh, I was interested in it anyway. But what gave me the time? Here's what it was. I used to be around the quarter system. And the first quarter would end at Thanksgiving, and before Christmas there was that 3-week gap in there. In the year I was a senior, they had this thing called, what was it called? SIP, Student Interest Program, when you could, like co-oping, you could go get a job. Most people went down to their parents' office and helped out, or their parents said they went down to their parents' office and helped out. I don't know. About 2/3 of my classmates did something. Me? I didn't have anything to do. I went to school. And we didn't really have classes. So what did I do? I went to the library, Woodward Academy's library. And I checked out books like space-time physics and something else. And looked at all these little space-time diagrams and thought and got where I could understand it. It was fascinating. And then people came back to school. We did the other stuff. I guess we had a little bit about that in class. But then I went to tech. And at some point, I took relativity again. I had to dredge it back up a couple of times. Then it kind of slips out. But then when I started teaching it, then it stuck and I love it. So I'm going to try to convey it to you best I can. Here goes. This example is, come on, right. Here we go. This is a giant mirror, a huge mirror. And this is a spaceship. See, little fins on it. Going that way, that's a spaceship. In the spaceship is a mad scientist, complete with lab coat. Stereotypical mad scientist hair. And he has a laser. And he is a distance of 186,000 miles. Well, 1 light second from the mirror. Now, he doesn't think he's moving. It's only making him not be moving for a minute. So he shoots. Yeah, he doesn't think he's moving. In a mirror, can you tell if a mirror's moving? Doesn't really, just looks like a mirror. It doesn't really matter if it's moving or not. He shoots the laser beam down in the mirror. It hits the mirror and it bounces right back and comes back to him. And he has a clock or a stopwatch. He times how long it's gone. I think you know how long it's going to be gone. It goes down to the mirror, back up. That is a round trip of 2 light seconds, which obviously takes 2 seconds. So he says, 2 seconds in his stereotypical, mad scientist voice. That pair of events, the emission of the light from his laser and the reception back at the laser, was obviously 2 seconds. However, I said he's flying relative to the mirror, or at least relative to somebody else. He's going this way. I want him to be going 0.6 c. He's traveling 6/10 the speed of light. It's a number that works out well. Down on the mirror, let me just show what it looks like first. If he does this, then the light is going to take a path like that. That is pretty obvious. There's not really much of a way around that. Obviously, that is very, very definitely a longer path. In fact, it's a nice Pythagorean theorem-y kind of thing. In fact, I'm doing some Pythagorean 3, 4, 5 triangle triple things here. Anyway, the light obviously travels further. Now, common sense, it's fun when that doesn't work. Common sense tells you that since this is a longer path, it must have gone faster. Vector addition. See, you're going to have like your horizontal component, your vertical component, you're going to add them up, get a bigger component. So you say, look, the light's going faster than the speed of light. Because obviously the time it takes has got to be the same, right? I've got a mental image of this, dribbling a basketball. What if you just love basketball so much you just can't ever quit dribbling? Everybody knows you as the dribbler or whatever. And so you're dribbling, it could be like whatever. Anyway, you dribble the basketball. And when you go to the airport and get on the people mover, the moving sidewalk thing, you just dribble the basketball the whole time. Somebody watching you dribble is going to see the ball do like that. They're going to, obviously, if you're dribbling the ball once a second, they're going to see you dribbling once a second. And you think you're dribbling once per second, right? And you perceive the ball to have these components of velocity. They perceive them to have those and this one. And so they see it going faster. What gives? The speed gives. Because obviously the time's the same. And obviously the distance is different. If the distance is greater and the time's the same, you got to go faster. Oops, not here. Because we just said speed of light's the same for everybody. So the light can't go faster than the speed of light. If it doesn't go faster than the speed of light, but it went further, it had to, take longer. Who thinks it takes longer? This person. It's another mad scientist. This will be a female mad scientist who doesn't have male pattern baldness. Okay? She has a clock. She sees it go further. The way I've got the numbers going here, this is a distance of 1.25 light seconds, and so is this. So she sees it light seconds. So she sees it go 2.5 light seconds of distance at the speed of light, which takes 2.5 seconds. So she clearly says 2.5 seconds in her mad scientist voice. Oh gosh, we got an issue here. He says that 2 events happen 2 seconds apart. She says they happen 2.5 seconds apart. And you know what? They could be talking to each other during this. They could be having a conversation. He could be counting. He could be counting like out loud. It's like 1,001, 1,002. And she would hear that take longer. And it would sound something like 1,001. To that. She'd hear him all slowed down, like she's thinking like, ooh, weird. He's like aging slowly. Strange. But she maybe understands it because she knows about relativity. You see how this had to happen, right? You had to get this thing called time dilation because of a what gives issue. Time dilation. Because if the speed of light is going to be the same for everybody, and basically, distance equals speed times time, but the speed can't change, then obviously, how does this work? You travel greater distance, it had to take a longer time. So it did. You might think at this point, aha, I've resolved the twin paradox. Weird, but I get it. Not yet. You don't get it yet, because here's the thing. What about how she sounds to him? I would think you would say Oh, well, she hears him talking too slowly. He must hear her talking like a chipmunk, too fast. Symmetry, because motion is relative. If I were to have her think he was talking too slow and him kind of agree by saying, yeah, no, like you're talking too fast, then I would have blown symmetry and I would know who was moving. It'd be him, right? We got to go to his world where he thinks, oh, well, let me show you this. She has a laser and a stopwatch. He has a mirror mounted on the bottom of the spaceship. And so she shoots a laser straight up, which hits his spaceship's mirror as it passes by and bounces right back down to her. And she says that took 2 seconds. But in his world, he's going to see it come up at him and go down behind him like that. He's going to see it take a 2.5 light second long path. He's going to see it do this in his world. And he'll say that took 2.5 seconds. He'll accuse her of talking too slow. So we got this weird thing where 2 people are each accusing the other one of talking too slowly. One of them says, you're talking too slow, which comes across sounding like, you're talking too slow. What's the old saying? Pot calling the kettle black, something like that, like, well, me, you're the one who's talking too slow. No, you are. I know you are, but what do I do? Something like that. So we got a problem. This is not the story of the twin paradox that I told. I told a story where 2 identical twins were really drastically different ages. You can't get one of those polite things, like 2 people get together after a long time and, in the South, you could get this sometimes. Oh my goodness, you just have not changed a bit. Oh, no, me? Oh, no, you're not the one getting my body out of bed in the morning. You're the one who hasn't changed a bit. No, you. And they get a big argument, over who looks younger. That's not my story. I'm saying one of them's really 100, one of them's really, still 20. So we're not there yet. We're going to get there. On the way, I got to show you 2 more things. I can't make this video last forever. I'll have to have another one. But let me show you a couple more things. There's more than just time dilation going on. Now I want you to see what happens if one of them, this picture's getting a little messy, but if one of them has a meter stick, or a stick, might be longer than a meter. What if there is a stick that, let's say, who's going to hold this stick? She's holding the stick. She has a 3rd giant robotic arm that comes out and she's holding the stick with it. And this stick is just right so that she sees him fly by this stick during the same time she sees the laser go down and back up. So she is going to say that the stick is, how long? Okay, we think for a second. She's going to see it take 2.5 seconds. And she sees him going 0.6 C. So it's 0.6 times 2.5 is 1.5 light seconds long. That is the length of the stick. As he flies by at 0.6 the speed of light, taking 2.5 seconds, he must travel this distance, 1.5 light seconds, and by definition, the way I define things, that is how long the stick is. So she says the stick is 1.5 light seconds long. What does he say? He thinks it took 2 seconds for the stick to fly past him at 0.6 C, which is the relative speed, and that counts, they both say that. So he says it's 1. Her. He says, she says, him, or should I say, she and he. What case am I using? Okay. Anyway, it's going to be 1.2 seconds. Well, my goodness. Now we have another Einsteinian weirdness here, relativistic effect. It's called length contraction. Length contraction. Need a contraction for that. Length contraction is when you see somebody fly by you, they appear compressed along the direction of motion. If somebody runs by you at 0.6 C with a meter stick, you will see it being 0.8 meters long. Is it 0.8 meters long? The owner of the meter stick doesn't think so. They think it's 1 meter long. And maybe if you held the same stick, you'd think so too. But you measured that as best you could as it flew by, and it was 0.8 meters long. So you see everything contracted along the direction of motion by the same factor that that other thing happened. By the way, that factor, I'm going to say it. I'm going to go do the math. Well, I'm not going to do the math right now. I don't feel like deriving stuff right now. But I will say it's a Pythagorean theorem thing having to do with that triangle right there. You do your little bit of algebra. It's not even calculus. It's just algebra. And you get this factor called gamma. And gamma is 1 over the square root of 1 minus beta squared. I like to say beta because it's quicker than writing V over C. I'm defining beta as being the fraction of the speed of light. Now, this is a number. If you plug in beta of 0, meaning you're not moving or no relative motion, then you get a gamma of 1, which means nothing weird. You just multiply the length by 1, or divide by 1. Multiply the time by 1, it's just 1. But you'll find the behavior of this thing when you get up to 0.6c, you get 1 minus 0.36, that's 0.64 squared, it's 0.8. Yep. Gamma is 1.25 when beta is 0.6. And it grows rapidly as you get closer and closer to C, or to beta equals 1. For example, when you get a beta of 0.866, this goes up to 2. And when you get a 90.99, you're up to 7.07. So this factor blows up as you get close to the speed of light, up to infinity at the speed of light. That's the behavior of gamma. But there's one more weird gamma thing. This one takes a little bit of care in explaining. I had to work on this explanation a little bit. It's a little bit contrived. But I'm going to do it. And I'll say more about it later. I'll shut up on this video in just a few minutes. But let me get this now. Okay, so as they fly past, imagine this. What if he wants to throw a ball at her instead of a laser? He throws a ball. So as he flies by, he's going to throw a ball. He thinks the ball's going straight down. He threw it straight down in his frame of reference. It's got some mass and some speed, so it's got some momentum. The momentum he thinks it has depends on how fast he thinks he threw it. Now, she is going to, in perfect symmetry, also throw a ball in such a way, this is tough to pull off. I mean, kudos to you if you can fly by me and I throw, kudos to me too. If we throw a ball and they actually bounce off each other. But they do. So she throws a ball upward. He throws the ball downward, but in her world it goes like this. So those two balls collide. And let's say they bought them at the same store. It's the same brand of ball, all that. So this ball's going to bounce off and go back up. And what I want to have happen, I'm engineering this carefully so that the balls collide midway, symmetry, and they each bounce back to their respective owner. Perfectly elastic collision, got them at the elastic store, whatever. And so think about what she must think about the ball he threw. She sees it hit her ball and come back. It's the same brand of ball and everything. She sees it, though, going slowly. Remember, she sees him in slow motion. She sees him talking too slow. So she's going to think you threw the ball more slowly and it takes a long time to get back to him. How are you going to account for what's apparently a symmetrical elastic collision like that? How are you going to account for that if he threw the ball too slowly? They had to have equal momenta along the y direction to come back. But it's going slowly. Momentum is mv. Well, there's one way to make sense of it. If the v is slow, the mass better be big. If you think the ball he threw was going slowly, you're going to have to believe that it's more massive. So we have yet one more gamma thing, and that is that the mass is gamma times what I'm going to call the rest mass. When you bought it at the store, and then it was at rest relative to you, that ball had a mass called its rest mass. And now it's got more mass. It's the only way you're going to make sense of it. Now, there's plenty more to say about that, but what we've done here is I've introduced, the whole idea of why Einstein got worried about this stuff and how this is going to go and postulates and 3 weird tricks. First of all, the time dilation, then the length contraction, and then some weird mass increase. I'll have more to say about that mass increase too. It ties into some neat stuff. Okay, that's enough for now. I'll do a follow-up video later.